So welcome back to week 5 of the thermodynamics course. Uh, Basically the problem solving session for the thermodynamics course. And as per our regular agenda, we'll go through the topics that were discussed by Professor Anand in this week's lectures. Of course, I will not dive deep into each and every topic, but just skim through it briefly, discuss I will very briefly discuss the topics that were discussed by Professor Anand in the lectures. And if you have any doubt, you can ask. I will try my best to solve them or make you understand them in a better way. But else, if you are not able to understand even after that, you can just put that out in discussion forum so that we can work upon it even after today's session. And finally, it would, if you are not able to understand the topics that are discussed today, or if I'm not able to clarify the topics that were your doubts properly, you can go back to the lecture of Professor Anand. I think they are the best source for knowledge for me as well as all the other students in the session. And also you can refer the books that were suggested by Professor Anand in the start of this course. That is book by Stephen Turns and P.K. Nak. So with that brief overview, let's start with today's session. Okay, so in this week's session we will be primarily discussing about the mass fraction, the volume fraction in a mixture of gases. Basically we'll try to observe or understand how to analyze a mixture of gases, or how to analyze the thermodynamic properties of a mixture of gases. We will be introduced to the Dalton's law of partial pressures, or Amagat's law of partial volumes. So we will look upon it as well. And with that overview for today's session, let's start our discussion. Okay, so the first statement is, as discussed by Professor Anand, is that the specific heat ratio, that is gamma basically means gamma is equal to Cp by Cv. The specific heat ratio of it is the ratio of the specific heat at constant pressure over the specific heat at constant volume. And it is mentioned that the specific heat ratio gamma reduces with the increase in the temperature for air, carbon dioxide and argon. So air is a mixture of gases, carbon dioxide is a triatomic gas, and argon is a monoatomic gas. So air in its essence is actually a mixture of gases and should ideally be dealt as a mixture of, as a function of mixture of gases rather than a ideal gas implicitly. But to make our thermodynamic analysis much more simpler, because air is a type of fluid that has vast application. Okay, that is used in our as a thermodynamic fuel in our day-to-day life activities and day-to-day life applications, as well as equipments. So in order to save us with the tedious task of analyzing these systems, or analyzing air as a mixture of gases rather than as an ideal gas, we consider, to simplify our calculations, we consider air to be simply be an ideal gas, and we consider it to follow the ideal gas law. Okay, of course under certain assumptions, but ideally for most of the cases we consider air to be an ideal gas, and then we carry forward our calculations. But in this week's session, we will be discussing about how to analyze systems, thermodynamic systems that comprises of multiple types of gases. Okay, and how this mixture of gases affect the thermodynamic properties, and how they show their behavior based upon their concentration levels in the mixture. Okay, so Professor Anand rightly discusses about these three types of gases: air, which can be considered as an ideal gas; carbon dioxide, that can be considered as a triatomic gas; and argon, that can be considered as a monoatomic gas. Okay. For perfect gases, basically it means perfect gases, therefore the types of gases where the value of these specific heat ratio, the specific heat constants, uh, the the specific heats, the Cp and Cv remain constant. Okay, they are not a function of temperature and they actually are independent of temperature. But still, the relation that is Cp minus Cv by is equal to R holds quite appropriately in these cases as well. So you can clearly see that both Cp and Cv are independent of the temperature and are basically a straight horizontal line in the specific heat versus temperature plot. Okay, but still they hold the difference of R between them. Okay, that's basically if we take the value of Cp for some certain temperature and Cv for certain temperature, you will find that Cp minus Cv will give you a constant value, that is R. This is the specific heat ratio, sorry, the specific gas constant for a particular gas. Okay. For example, in the case of air, it comes out to be around 0.287 R. Air is 0.287 kilojoule per kg Kelvin. Just an example, and it will depend upon different types of gases. Okay, and for ideal gases, these Cp and Cv, both Cp and Cv are actually are functions of temperature. Okay, and if we are going to plot, say, the enthalpy versus entropy plot for these semi-perfect gases or ideal gases, we'll get that this enthalpy versus entropy plot will give us a curved line, because see, Cv itself is a function of temperature, and since we're plotting it since we define enthalpy as, sorry, internal energy as, oh, I'm extremely sorry, I guess I initially announced U as entropy. It's not entropy, it's actually internal energy enthalpy. Okay, so if you're going to plot this internal energy and enthalpy plot versus temperature for ideal gases or semi-perfect gases, where Cp and Cv both are functions of temperature, you will see that the enthalpy and internal energy plot will give us curved lines. Why? Because primarily, since Cv and Cp both are functions of temperature, and we know that by definition U is equal to Cv into T and H is equal to Cp into T, and since there's a product between these two functions of temperature, we'll get some curved line rather than it being a straight line, which is in the case of a calorically perfect gas or or a perfect gas, as I mentioned, where we see that if you plot the internal energy and enthalpy plot versus temperature, we'll see that you will get a straight line, which is basically where the Cp and Cv gives the slope of this line, which has an intercept, which is a y-intercept of 0. Okay, basically it acts as an equation of straight line, like say if y equal to mx, and if m is a constant, then it's basically a straight line. Okay, so since Cp and Cv both are constants in the case of perfect gases, we will get the plots of enthalpy and internal energy as straight lines. The plot of internal energy and enthalpy as straight lines in the internal energy versus temperature plots, or enthalpy versus temperature plot. Okay, so now let's consider a system of mixture of gases. Okay, so Professor Anand took again the example of air itself, because that's something that is most easy to relate with. I'm sorry. Okay, so air here is primarily a mixture of nitrogen and oxygen. Why? Because nitrogen consists of 78% of the entire the air is composed of 78% of nitrogen, 21% of oxygen, and 1% of other gases, and we are just disregarding this 1%. Okay, just we are disregarding this 1%, and since the primary components of air are both nitrogen and oxygen, we are considering air to be primarily a mixture of nitrogen and oxygen. Okay, so now if, and in these cases, air can be considered as a bicomponent mixture, right? Bicomponent means it's a mixture of two different types of gases. So say if in a closed enclosure, if you're having air within a closed enclosure, then say the nitrogen is the mass of nitrogen in that mixture of air is equal to m1, and mass of oxygen is in this mixture is m2. Now similarly, if we are consider n, say the number of moles of nitrogen in that mixture is n1 and number of moles of oxygen is n2, then the total number of moles of gas in the this mixture is, that is enclosed within the enclosure, is n is equal to n1 plus n2. Similarly, the total mass of gas within this mixture can be given by m is equal to m1 plus m2. And now if we want to generalize this notation, say for n number of gases, because there are instances where we will be dealing with say 2, 3, 4, 5, and say no, a mixture of n number of gases, right? And ideally, again, if you want to be thermodynamically more accurate, then air can be considered to be a mixture of many different types of gases, right? Not carbon dioxide, argon, water vapor. Then there are different types of gases, right? Sulfur dioxide. So of course the amount of these gases are negligible, but still, if you want to be even thermodynamically more accurate, then we have to consider these the effect of the concentration of these gases as well, however small they may be, right? So in that case, then you can consider air to be a composition of n number of gases, but ideally you can just consider it to be bicomponent mixture of gases, which is basically nitrogen and oxygen. But say if we are given a question, or we are given a scenario where we are dealing with a system that consists n number of gases, then in that case the the total number of moles in that enclosure that encloses this mixture of n number of gases will be given by n is equal to n1 plus n1 plus n2 plus n3 dot plus nn, where n is the total number of gases. Or in a simple compact notation, we can write it as a summation of ni, where I varies from 1 to n, where I is the index that denotes the particular type of gas. Okay. Now similarly, the total mass can be given by m1 plus m2 plus m3 plus plus mn, where this can again be written in a compact form as summation of mi, where I varies from 1 to n, capital N, where n denotes the total number of gases in the mixture. Okay. Now we define two very important parameters, okay, or two very important properties of these two types of two important properties of these types of mixture of gases. First is the mole fraction, and second is the mass fraction. Where mole fraction is basically the ratio of the number of moles of a particular type of gas or the total number of moles of gases in the mixture. So it can be written as xi is a mole fraction for a particular gas, say denoted by the index I, where xi will be given by ni over the summation of nj, where j varies from 1 to n. Okay, and this will basically be equal to n, so we can write xi is equal to ni by n. Similarly, we can I'm sorry, just 1 minute. Similarly, the mass fraction can be defined as the ratio of mi over summation of mj, where j varies from 1 to n. Okay, so this summation of mj, where j varies from 1 to n, will basically give us m, where m is the total mass of gases in the mixture. Okay, and the numerator mi denotes the mass of a particular type of gas whose mass fraction we are going to evaluate. Okay. So I hope this definition was clear. And now by a very mathematical definition, we get that it's very trivial to derive, but I'm not going to derive it. It was derived by Professor Anand in the classes. So we get that summation of all the mole fraction, that is xi, summation of xi where I varies from 1 to n will be equal to 1. Similarly, the summation of all mass fraction where I varies from 1 to n will be equal to 1. Okay, it's a good exercise. You can prove it, say considering a two component mixture. Very simple, quite trivial. So example, if you don't want to do it, but say your y1 is m1 by m1 plus m2, and considering a two component mixture, okay, the case that we are say started with, the mixture of air nitrogen. So if I want to evaluate y1 plus y2, it will basically be m1 divided by m1 plus m2 plus m2 divided by m1 plus m2. Now since the denominator is the same, we can add up the numerators, so we'll get m1 plus m2 divided by m1 plus m2, this will be equal to 1. Now we can extend it to n number of gases, but it's just a lengthy task to do. But you can derive for two components, then you will get the same result for say 3, 4, 5 n number of gases. Okay, that's quite easy to prove, but just saying as an exercise you can try that, but you get the same thing. Okay? And I don't think there should be any doubt regarding that. Okay, so I will give you 1 minute to just digest the topics that we've discussed till now, say the definition of a mixture of gas, definition of mole fraction and mass fraction. So these definitions are something that you should be well versed, because you will be dealing with some manipulations of these definitions in the later part of today's discussion. Okay, I'll give you 1 minute to go through these definitions or calculations even if needed, and then we can proceed. Okay. Okay, then I think we can proceed. So Professor Anand again took the liberty to simplify it even further. For example, he literally told he's showing us the mass fraction of this component this composition of mixture of gases that we're considering. Just 1 minute. Okay, so for example, let us find the mole fraction of nitrogen in the case of the mixture of nitrogen and oxygen. Okay, basically the mixture of air that the air that is air enclosed within the container that we are considering right now. Okay, so the mole fraction of nitrogen, say we are considering denoting nitrogen as index 1, then x1 is equal to xn2. That will give us n1 divided by n1 plus n2. Similarly, the mass fraction of nitrogen, or y1, is equal to yn2 will be given by m1 divided by m1 plus m1. Similarly, in the case of oxygen, it will basically be n2 by n1 plus it will be n and y2 is equal to m2 by m1 plus m2. Okay, now we know that, alright, let me just define it. Like, to find the number of moles of a particular type of gas in a mixture, or by simple definition of how to find the number of moles of a gas in a mixture, it can be defined as number of moles n is given by the total mass of the, say I'm doing for a particular gas indexed by 1, then n1 will give it by the total mass of the gas in the mixture divided by the molecular mass of the mixture. Sorry, molecular mass of the gas of that particular gas. Okay, in other words, we can write small m1 is equal to small n1 into capital M1. Okay, please forgive me if your getting confused with small m and capital M, I try my best to make you understand, but there may be instances where you can get confused, but I'm sorry for that. I'll make sure that I pronounce or enunciate the differences clearly whenever I'm going to handle these two different types of masses. That is, first is the total mass and second is the molecular mass. But still, if you have any doubt, you can please ask me. Okay, you're not able to follow. Sorry, you're not able to follow the discussion. Okay. Now, yes. So if we are considering, say, an n component mixture of gases, then say for the first gas, that is m1, then m1 will be given by n1 into m1, where it is m1 is the molecular mass of that particular gas. Okay, and this is capital M1. Similarly, small m2 would be n2 into capital M2. Similarly, dot 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 mi, a general notation for mass of a particular gas, would be ni, this is the number of moles of that particular gas, into mi, this is basically the molecular mass of that particular gas. Or for n component system, that is mn will be given by nn, where n is the small n is the used to denote the number of moles of that particular gas, and n is used to denote the particular index for the particular component whose number of moles we are evaluating, where mn will be equal to small nn into capital Mn. Okay. Again, forgive me if I'm making you confused regarding the small n, capital M, small n. But just request that you bear with me and go through the session. Okay. Then small m, there is a mass of the total mixture will be given by summation of mi, I varies from 1 to n. Okay. We just discussed it. So since m1 is n1 into m1, m2 is n2 into m2, then if we substitute this mi as m1 plus m2 plus m3 plus dot 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 plus mn, m, it's all m are small n, it's all m's are small letter m. Then if we substitute m1 as n1 into capital M1, n2 is equal to into capital M2, then we will get that this small m would be equal to summation of ni mi, where I varies from 1 to n. It's the first manipulation that we have done to the equations that we have in our hand. Okay. Similarly, if you want to find out yi, where yi is basically the ratio of mi, small mi over small m, this is the mass of a particular gas over the mass of the total mixture of gas, then it can be written as xi into mi over summation of xi mi, where I varies from 1 to n. Okay. How we derived it? I guess this was discussed by Professor Anand as well in the lectures. So, for example, we consider this ratio, okay, mi over n. So mi is ni into mi from these relations. Then ni in over n would give us the mole fraction xi. Then mi by n would give us xi into mi. Similarly, m over n is equal to summation of ni into mi over n or summation of xi into mi, because ni by n will give you xi. Okay, so mi over m, which is basically equal to yi, would give you summation of xi by mi, there is a numerator here, over summation of, sorry, will give you the numerator as xi mi and the denominator as summation of xi into mi. Okay, the units of number of moles is usually taken to be kilomole, and the units of molecular mass is usually taken to be kg per kilomole. Then their product, kilomole into kg per kilomole, will give us a unit of mass or equal to kg. So it's a good practice. I would suggest that if you are able to recall the units of this part of all these properties that we are discussing in today's session. For example, what's the unit of molecular mass, what's the unit of number of moles, and so it's a good practice to do, but of course not necessary, you'll eventually get the hang of it. But if you're able to recollect all these units, then what would happen is that, for example, if you're doing some particular numerical manipulation of these equations, say that is required to solve a particular problem, then you will be able to cross verify your manipulations and whether they're correct or not. Because if they're incorrect, the units of the particular quantity that we are going to evaluate will not match. For example, if you are going to find the mass of the mixture in the gas, and after the mathematical manipulations that you have done to your equations, you find that the units of your final answer is something as kg per meter cube, then it's basically the units of density, and you're willing to find the mass of the mass as your final solution, then you can clearly understand that your answer is incorrect. Okay? It's a good practice actually. As engineers, it's suggested that you are well versed with the units of most of the physical quantities that you're dealing with, but of course it's not a necessity. You will eventually get the hang of it, but it is something that you can focus upon. Okay. Now let us consider a special case. For m equal to 1, okay, again, for sake of saving time, I'm not going to enunciate each and every line, so I'll give you the statement. Even the derivations are also given in the slide, so you can go through the derivations once after today's session when I upload the this presentation, and then you can verify your results. Okay, so for m equal to 1, that is, if we are considering, we know that n1 can be given as the number of the total mass divided by the molecular mass. Okay, so now if we are considering this quantity, okay, say y1 over m1, okay, and y1 will basically be, let me just write it, and y1 would basically be some mass m1 by total m. Okay, so y1 by m1 would be equal to mass m1 by small m1 divided by capital M1. Now in this ratio, if the total mass m is equal to 1, okay, the mass of the total mixture is equal to 1, mass of the mixture is equal to 1, then you will get that n1 is basically equal to y1 by m1. So keeping that consideration in these derivations, you can write n1 is equal to y1 by m1. The important thing to note is that it is not true every time. Okay, I'm just saying a special case where the mass of the mixture is equal to 1 kg. Then in that scenario, the mass fraction y will basically denote the mass of the individual gas in the mixture of gases. Okay, so we can write n1 as y1 by m1, n2 as y2 by m2. Basically we are interchanging m with small y, small m with small y. Okay, for a special case m equal to 1, and then only this relation holds valid. Now we know that small n is equal to summation of ni, where I varies from 1 to capital N. Okay, or since we know that n is given by yi by mi, ni is given by yi by mi, then we can write small n is equal to summation of yi by mi, where I varies from 1 to n. Okay, or the mole fraction xi is given by ni by n, which will basically be given by, now ni is yi by mi over summation of yj by mj, where j varies from 1 to n. Okay, to indicate this value. Okay, so see, in here you will see that you are using different index notations for the numerator and denominator. It's just to mitigate any kind of confusion that people may have having similar indices in both the numerator and the denominator, where one of the indices is going over summation. Okay, it's usually such kind of indices are usually termed as repeating indices, but just to remove the confusion, we are denoting it as separate indices in the numerator and denominator, where one of the indices has summation going over it. Okay, one more special result is that the molecular mass of the mixture, okay,
the molecular weight of the mixture can be found out by this equation. Okay, so I have derived the relation in this presentation. So as an exercise, I will suggest that right now, if you are willing, you can also even go ahead and derive this relation with your pen and pencil or iPad, wherever you are taking your notes. You can derive this relation. Of course, this relation holds when we are considering the special case of the mass of a mixture being equal to 1. Okay, and this one especially holds when we are considering the number of moles of the mixture being equal to 1. Okay, so keeping that idea in mind, you can derive this expression now if you want, or else you can just go to the derivation. Okay, so so keeping this consideration, we will get a conclusion that the mass of the mixture can be found out by this relation. Okay, sorry, the molecular weight of the mixture can be found out by this relation, where capital M denotes the molecular weight and Y denotes the mass fraction. Okay, of a particular gas that we are considering. Yi denotes the mass fraction of the gas, ith gas component. Okay, now there are two laws that can be that we are going to introduce. That is, first is Dalton's law of partial pressure, and second is Avogadro's law of partial volumes. So Dalton's law of partial pressure, if I recall, was briefly introduced in class 12 chemistry, where where we were studying about the solutions, second chapter in the first book. So I recall that, so I'm mentioning about it, giving a brief overview of where you might have heard about it. And Avogadro's law, like it's, and then we're introducing one new law, this Avogadro's law of partial volumes. Okay, so the derivation of this again are given in the lectures. I will derive one of them for you. So the I will derive the Dalton's law of partial pressure. Okay, so the Dalton's law of partial pressure states that the ratio of the pressure exerted by a particular gas in the mixture over the total pressure is actually equal to the mole fraction of that particular gas in the mixture. Or basically, if I'm going to find Pi by P, we'll get that Pi by P is actually equal to Xi, or Pi by P is equal to Ni by N is equal to Xi. Okay, and similar conclusion can be derived for the Avogadro's law of partial volumes, where Vi by V turns out to be equal to Xi, or Vi by V turns out to be equal to Ni by N, that it is equal to Xi. Okay, so let us now derive the Dalton's law of partial pressure. So let us consider the ideal gas law for a n component system. Okay, so where there are n number of gases, so I'm applying the I'm applying the ideal gas law for all these individual components. Okay, so I can write the ideal gas law for the first component as P1V equal to N1 R bar T. The temperature and the volume are constant for all these gas components. Okay, and it is the pressure exerted by this gas component that is different in the mixture. Okay, this is the differentiating parameter of this mixture of gases. Okay, now similarly, we can write for the second component of the gas as P2 in the ideal gas law for the second component as P2 into V is equal to N2 R bar T. Similarly, for the ith component, we can write Pi V into Ni R bar is equal to Ni R bar into T, where R bar denotes the universal gas constant. Now, the total pressure P is actually the summation of all this pressure exerted by the individual gas components. Sorry for this. So, for the entire mixture, we can write the ideal gas law as PV is equal to N into R bar into T, where T is the temperature, V is the volume occupied by these gases, P is the pressure exerted by the total pressure exerted by these individual mixed components of gases in the mixture, and N is the total number of moles of these gases in the mixture. Okay, now from this equation, I can write Ni is equal to Pi into V by R bar into T, and from this equation I can write N is equal to PV over R bar into T. Now we know that xi is equal to ni by n. This is the very definition of mole fraction. Then from that, if we substitute the value of ni and n, we will get that xi is equal to pi over p. Now similar analogies can be used to derive the Amagar's law of partial volumes. From that you will get the same relation. You need to use the ideal gas law for the Amagar's law. Similarly, now we impose that instead of the volumes being the constant parameter for this mixture of gases, individual mixture of components of this mixture, we impose that these individual components of gases exert the same pressure in the container that holds this mixture of gases. Okay, so in that, and it is the variable parameter in this case is actually the volume occupied by these individual components of gases. Okay, so the, using similar analogy, we can define the ideal gas law for each and individual gas components. We'll keep the pressure and the temperature as constant and use the same analogy to derive this expression. Okay, now let us just give me 2 minutes. I'm just having a trouble with my nose. So I'll handle it once and then we can return back. Okay, so meanwhile you can just look into the derivation if you want. If you have any confusion, you can ask me. Meanwhile, I will just come back in 2 minutes. Sorry for the confusion. Okay, then I guess we can move ahead. So now we deal with the thermodynamic properties of internal energy and enthalpy for this mixture of gases. Okay, now if we consider, say, the total internal energy of this mixture of gases, okay, then this can be given by the product of the mass of each of these individual gas components multiplied with the internal energy of the particular mass of gas in the mixture. So U1 basically denotes the specific internal energy of that particular gas element, I would say the particular type of gas in the mixture. Okay, so if you're considering, say, mixture of O2, N2, CO2, say, and there are other gases, so U1 is the specific internal energy of oxygen in the mixture. U2 is the specific internal energy of nitrogen in the mixture. UI, say, or U3 is the specific internal energy of the carbon dioxide in the mixture that we are considering. So similarly, then there are n number of gases, so UN denotes the specific internal energy of that particular gas type in the mixture. Similarly, M1, M2, M3 dot 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 Mn denotes the mass of this particular gas type in the mixture. Okay, so the total internal energy of the mixture can be given by the summation of mi ui, or small mi into small ui, where I varies from 1 to n. Okay, similar summation symbol that we used while defining the total mass or total number of moles in the mixture. So the small u can be given by capital U over m, or we can write summation of mi ui over small m, where I varies from 1 to n. Now if I consider this, the ratio of small mi over small m, we know that small m, the ratio of small mi over small m gives us the mass fraction. Okay, so we can write u, small u, or specific internal energy of the entire mixture as the summation of yi into ui, where yi is the mass fraction and ui is a specific internal energy, and I denotes the I is used to denote I is the index used to denote the particular gas whose say specific internal energy or mass we are going to want to evaluate. Okay, so the specific internal energy of the entire mixture now can be given as the summation of yi into ui, where I varies from 1 to n. With similar analogy, we can also define the specific enthalpy of this mixture as summation of yi into hi, where I varies from 1 to n. Okay. uh, with sorry, with the similar concept in our head, we can again deal with the molar specific enthalpies as well. Okay, I'm sorry, there has been a typing mistake. So it would be smaller, sorry, molar specific internal energy. Okay. Sorry, I'm having bit of trouble in with my nose. I'm having a suffering with a bit cold. So sometimes my words may be a bit confusing. So I apologize for that confusion that my uh, sinuses may create while I'm explaining something. Okay, I apologize for that. So the total internal energy, capital U, can be given as a product of N1 into U1 bar, N2 into U2 bar, where U1 bar denotes the uh, the molar specific internal energy of a particular gas type in the mixture. Okay, so capital U can be given as N1 into U1 bar plus N2 into U2 bar dot 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 N into capital UN bar. So in the form of summation, we can write, sorry, in the form of summation, we can write capital U as summation of Ni into Ui bar is capital U. Okay, capital Ui bar, where I varies from 1 to n. Okay, now again with this, from this relation we can write U bar, capital U bar as capital U over small n, or the summation of Ni into Ui bar over n, where I varies from 1 to n. Now we know that Ni over n gives us the mole fraction of that particular gas type. Then we can write U bar as summation of Xi into Ui bar, or Xi into capital Ui bar, where I varies from 1 to n. Okay, and a similar understanding we can also define capital H bar, or the molar specific enthalpy, now as the summation of Xi into Hi bar, capital Hi bar, where I varies from 1 to n. Okay, considering that we are dealing with an n system of mixture of n number of gases. Okay, similar derivations can be found for the molar specific heat for constant pressure, molar specific heat for constant volume, that is given by these expressions. And with that idea in mind, we can also define the specific heat ratio as Cp over Cv, or again it can also be defined as Cp bar over Cv bar, where Cp bar denotes the molar specific heat at constant volume and Cv bar denotes the molar specific heat at constant volume. Having these definitions in with us, we can then define gamma, or the specific heat ratio, as the ratio of the summation of yi into Cpi over the ratio of the summation of yi into Cvi. Similarly, gamma can also be defined as the ratio of the summation of xi into Cpi bar over the ratio of the summation of xi into Cvi bar. Okay. Now let us consider one example. I think there have been lot of formulas and math in today's session, so, and it might be a bit overwhelming because we need to recall and recollect all these relations, and there might be some confusion initially. Now, of course, it's understandable. So let us take one example, and this example was again taken by Professor Anand in the lectures. So I will just reiterate it once. So if you have any doubt, you can stop me at that moment. So let us go through it once, so that all the topics that we discussed till now can be clarified. Okay. So let me read the question for once, and then I'll give you a few minutes, 2 minutes, 1 or 1.5 minutes to understand the structure of the question, and then decide which are the things that we need to evaluate first to get to the solution. Okay. So the question is, a cylinder contains 70 grams of oxygen and 300 grams of helium. The volume of the cylinder is 10 liter. Okay, the volume is given and the mass of the individual gas components are given. Okay, calculate the partial pressure and the volume of each gas and total pressure in the cylinder at 25 degrees Celsius. Okay, so I guess since there is the concept of partial pressure, I think we need to use the and as a volume as well, so we need to use the Amaker's law as well as Dalton's law. Okay, so it is given that the mass of oxygen is 70 gram or 0.07 kg, so mass of helium is 300 gram or 0.3 kg, okay, and the volume of the container is given to be 10 liter or 10 to 10 to minus 3 meter cube or 10 to the minus 2 meter cube. Okay, so it's wise to keep the units in a particular in a uniform system of units. So since we are dealing with SI units, so it's a good practice to deal with kg, meter cube and second, so that there is no confusion. Okay, and temperature is 298 Kelvin. Okay, we need to use the absolute temperature scale for evaluating the properties in the in this case of thermodynamics. Okay, so it's just a general practice. So since the mass of each and every gas component is already given, so you may think that we are asked to find the partial pressure, and we know the partial pressure varies as the mole fraction of these gas components, but there's no hint or clue to find the mole fraction in itself because you're not given the uh, molecular weight. Okay, so the molecular weight of the mixture, okay, you do not know how to find that. So because then only you can find, if you know the molecular weight of the mixture, then only you can find the total pressure in the cylinder. This is the pressure exerted by the mixture of gases rather than the individual gas components. Okay, so to deal with it, let us find the parameters that we can find with the values that we have already been given. Okay, since we already know the mass of individual gas components, we can find the mass fraction of these individual gas components. So YO2 will be given by MO2 over MO2 plus MHE. Then we'll get YO2 is then MO2 is 0.07 and MO2 plus MHE is 0.37, which gives us YO2 as 0.18, and YHE can easily be found out by replacing 0.07 with 0.3 or simply by subtracting 0.18 from YHE to from 1 to get YHE. Okay, because we know that YO2 plus YHE would be equal to 1, or summation of all the mass fractions and mass fractions will be equal to 1, and summation of all the mole fractions will also be equal to 1. Now from Dalton's law we know that PO2, the pressure exerted by O2 only, is equal to the mole fraction of O2 into the total pressure exerted by the mixture, and these two things we do not know right now. Okay, similarly the pressure exerted by helium is equal to the mole fraction of helium into the total pressure exerted by the mixture, and this can be derived or discussed from the Dalton's law of partial pressure. Okay, we know that molecular mass of oxygen is 32 kg per kilomole and molecular mass of helium is 4 kg per kilomole. So let us go back. So the molecular weight of the mixture can be found out from using this relation. Okay, that I already mentioned as an exercise for you to derive, like how to derive it. Okay, you go through the derivations I have given here. If you need it, you can put that out in the discussion forum, but I'm leaving it as an exercise for you to go through the derivation once and understand how you are going to derive it. Okay, the clue is to consider 1 mole of mixture. Okay, that's the clue that you can take as a starting point for the derivation. Okay, so now we have YO2. Sorry, I was a bit down here. So the mass of the molecular mass of the mixture can be found out by this formula. If you're able to recall it, that's very good. Otherwise, you can again go through several steps to find this relation. But it is something that holds good for any type of case. Okay. Now we know that M mix, the molecular mass of mixture, can be given by this relation. So we substitute the value of YO2, MO2, YHE, and MHE here. Then to get that, the mass of the mixture is 4.74 kg per kilomole. Okay. YO2 was 0.1 and YHE was 0.82. Then molecular mass of oxygen is 32 kg per kilomole, and molecular mass of weight of helium is 4. Okay, these are something that are good to be well versed with. Okay, so the weight of the mixture is coming out to be 4.74 kg per kilomole. Okay, units you need to verify all the time. Okay, since it's a molecular weight, not the actual weight, so it turns out to be in terms of kg into per kilomole. Okay, now the volume fraction of oxygen can be found out using this relation. Again, this is something that you can find out as an exercise. I'm not going to repeat it. So it is basically the ratio of the mass fraction over the molecular weight of that particular gas element into the molecular weight of the entire mixture. Okay, once you do that, you find that XO2 is equal to 0.18, it is the mass fraction of oxygen, 32, that is the molecular weight of oxygen, and 4.74 is the molecular weight of the mixture. From that you get that XO2 is equal to 0.026. Similarly, XHE can be found out by this relation, or either you can just subtract XO2 from 1. Okay, so XHE can also be found out as 1 minus XO2. Okay. We get that XHE is 0.974. Now we know that the total weight of the gas components is 0.37 kg, because MO2 plus MHE is equal to 0.37 kg. The volume of the mixture is 10 to the minus 2 meter cube, and temperature is 298 Kelvin. So from that you can easily find the pressure using the ideal gas law. Now let us find the volume of individual gas components, because this is something that we need to find. Okay, they asked us to find the partial pressure and the volume of each gas. So using Amagar's law, we can find that VO2 is equal to the is proportional to the mass mole fraction of this uh, gas component. So VO2 will be equal to 0.026 into 10 liter or 10 to the minus 2 meter cube, something that you can keep for free because they just ask us the value, right? So we can choose either to keep it in liter or meter cube, because we are not going to use to evaluate it any further, so you can keep it any units that you want. So ideally meter cube would be good, but you can keep it liter as well. Okay, and the volume of He, the total volume of He or helium is 10 liter into 0.0974 or 9.74 liter. Okay, now from the ideal gas law for the entire mixture, we can write P mix into V mix is equal to M mix into R mix into T mix, where R mix is the specific gas constant for the mixture. Okay, for the mixture, not the oxygen or the nitrogen, but not the oxygen or the helium, but the entire mixture of gas. Okay, the mass of molecular weight of the mixture is 0.37. This is something that we already found out. And like here, if we take the volume V mix as the denominator, you can you will get it as the I'm extremely sorry. Now if this is actually the mass of the mixture, not the molecular mass, so it's small m. Okay, this is why I was being confused. PV is equal to m multiplied by m is a small m. Okay? So it is a mass of the mixture. Now mass of the mixture is basically the sum of the mass of oxygen and sum of the mass of helium in the mixture. It's very simple. They were just you add up both the masses, you will get M mixture is 0.37 into R mix over V. So V is something that we take as a denominator. So we get R mix is 8.314 for okay. So again, I'm sorry for being stuck out. I was being confused why we are using this. So apologies for the confusion. So it is actually just it's my mistake that I didn't write the manipulation beforehand. Okay, so P mix can be written as M mix, small m mix, into R mix, R bar mix over M mix molecular, this is the molecular weight rather than the total weight, molecular mass or the total mass of the mixture. Okay, capital M into T mix by V mix. Okay, so 8.314 is the universal gas constant, right? So we can substitute R mix as universal gas constant because it's constant for each and every type of gas. So to find the specific gas constant for this particular mixture of gas, you divide it by the molecular weight of the gas, and that's how we evaluated the molecular weight of the gas, which turned out to be 4.74 kg per kilomole. Okay, just substitute the value of small m, that is 0.37. R mix, R bar mix, it is the universal gas constant. The molecular weight of the mixture, that is capital M. The temperature of the mixture is, that is 298 Kelvin, and the volume of the mixture is 10 to the minus 2 meter cube. Okay, so once you do that, you find that the pressure exerted by the entire mixture is actually 193 bar. And now it's not complete because we need to find the pressure exerted by each of these gas components, that is oxygen and helium. So we know that from Dalton's law of partial pressure, the pressure exerted by O2 would be equal to proportional to the volume fraction, sorry, the mass fraction of the oxygen in the mixture. So we can write PO2 as XO2 into P mix, or 0.026 into 19.3, or it is equal to 0.5018 megapascal. Similarly, pressure exerted by the helium is equal to the mass fraction of, so volume fraction, sorry, the mole fraction of the helium in the mixture into the total pressure exerted by the mixture. So we get 0.974 into 19.3, or 18.7982. So these are the mole fractions. Okay, not to get confused with mole fraction of oxygen and mole fraction of hydrogen from Dalton's law. Okay. So I'll skip this example and then directly go to this one, the the portion where Professor Anand has discussed some topics that where we go beyond the ideal gas. Okay, so here Professor Anand discusses about the behavior of isotherms in the case of ideal gases in a PV diagram. So he tells that for an ideal gas, a isothermal line in a PV plot would be denoted by a rectangular hyperbola. Why? Because from the ideal gas law we have PV is equal to MRT, or PV is equal to small P into small v is equal to RT. If we take the mass in the denominator here, it becomes a specific volume. Now, for a constant temperature, PV would be equal to constant because R is a constant. Okay. So we know that xy equal to c indicates a rectangular hyperbola in a y-x plane. Similarly, PV is equal to c, some constant c would denote rectangular hyperbola in the PV plot. Okay. With that mathematical analogy, we said that the isotherms in a PV plot will behave as a rectangular hyperbola in the case of an ideal gas. Okay. In the temperature volume plot, these constant pressure lines would be straight lines in the TV diagram. Okay. Again, you can just use the ideal gas law. Just manipulate the ideal gas law, like P small v is equal to RT, or T is equal to P by R into V. So your independent parameter is V, and specific volume, and the dependent parameter is T. So if you have constant pressure, it will basically tell us that the slope is constant and the specific volume in the temperature varies linearly with the specific volume in the case of ideal gas. Okay, and a constant and these straight lines denote the constant pressure lines in the TV plot. Okay, and for a perfect gas, Cp minus Cv is equal to R, that is a constant. So Cp and Cv are constants and do not depend on temperature. But for ideal gas, Cp and Cv both are functions of temperature, and if you are going to plot the Cp and Cv versus temperature variation, you will get that they will give you curved lines rather than being a straight line, because we do not know the relationship between Cv and T. It may also be linear, but in general it's not. So it is denoted by a curved line in the Cv into T plot. Cv by CV versus T plot or CP versus T plot respectively, and the integration of this integration of the area under the curve for CVT gives you the total internal energy for an ideal gas, and the area of the integral of of the integral of the area under the curve uh, of CPT gives you the total enthalpy in the case of ideal gas. Okay, and again they tend to have a same uniform difference even in the case of an ideal gas, that Cp minus Cv, even being a both of them being functions of temperature, would still maintain the constant difference of the specific gas constant R. Okay, so I hope this was clear. So let us now go and solve some questions. So this is the first question here. So which of the following is the correct statement for a Dalton's law of partial pressures? Okay, so I'll give you some time to look into the options and then you can tell me the correct answer. Okay, so here the correct answer is option B, that the pressure of a gas mixture is equal to the sum of the pressures that each gas would exert if it existed alone at a mixture temperature and volume. As I already mentioned while deriving the Dalton's law of partial pressure, that we need to keep the temperature and the volume constant for each gas. Okay, each and every gas component in the mixture. Okay, so let us go to the second question. It is a cold sunny day in Merrill, some US state, I don't know, and Wisconsin maybe. The temperature is minus 10 Fahrenheit. The barometric pressure shows out to be 100 kilopascal. Okay, oh, let me zoom in, then it would be much more clear. Okay, I'm sorry. Okay, just revisit the first question. The first question was, which of the following statement is the correct statement for Dalton's law of partial pressure? So the solution that we got was that the correct statement is the pressure of a gas mixture is equal to the sum of the pressures that each gas would exert if it existed alone at a mixture temperature and volume. So as I mentioned, when we were deriving the Dalton's law of partial pressure, we told that the partial pressure for each and every component, we keep the temperature and the volume of the gas exerted occupied by the gas to be constant in all the cases. Okay, so that's why we need to keep that. Okay, not at any temperature, okay, for that particular mixture temperature and volume. Okay, second question is, let me just clarify what does that mean. Okay, Wisconsin. Okay, Merrill, Wisconsin. it doesn't matter, just as a general knowledge you can know. It's a short form notation for Wisconsin, US state. Okay, it is a cold sunny day in Merrill, Wisconsin. The temperature is -10 Fahrenheit. Sorry. The barometric pressure is 100 kilopascal. Estimate the outside air density and also estimate the molar density N by V of the air. So molar density is defined by the number of moles over the volume of air. So you can, I guess, easily use the ideal gas law to find out density of the air and then find out the molar density of air in this particular weather condition. This -10 Fahrenheit temperature and 100 kilopascal barometric pressure. Okay, so let us look into the solution once. So that can be easily found out. It's quite simple. the the only key thing that is challenging in this case is to find the conversion of temperature between Fahrenheit and Kelvin. So this is the formula that is used to find out the temperature in terms of Kelvin when the temperature is given in terms of Fahrenheit. Okay, so temperature of air at Kelvin would be 5 by 9 into the temperature of air at Fahrenheit plus 459.67. Okay, so once you do that, you find that the temperature of air at Kelvin scale is 249 Kelvin, 249.8 Kelvin. Okay, we can take as 249 Kelvin. The density of air is given by rho is equal to P by RT, where rho is simply the density of air, and we use the ideal gas law to find it. To find it. So from that, if you substitute the value of P, R, and T with the correct units, you get that the density of air is 1.395 kg per meter cube. Okay. So the molar density is basically the number of moles per unit volume. Okay, or it's already given in the question. It's N by V. When N is the number of moles, it's given by small m over capital M. Now small m over V is the density, right? Mass, rho is defined as mass per unit volume. Sorry, rho is defined as mass per unit volume. So it, if you manipulate it a bit further, you easily get the molar density as density over the molecular weight of the mixture or the gas. Okay, so in this case you get N by V is equal to 1.395 over 28.97. That is the molecular weight of air. So you get the molar density as 0.048 kilomole per meter cube, because number of moles is in terms of kilomole and volume is in terms of meter cube, so the unit will be kilomole per meter cube. Okay, the next question is, show that for an ideal gas the slope of a constant volume process line on a TS diagram is more than that of a constant pressure line. Okay, so this is something that we'll eventually discuss in the later part of the course, but I thought that it would be interesting if we are introduced with this kind of concepts. But I think, like, just for the sake of not creating no further confusion, I will keep it as an exercise for a later problem solving sessions. Okay, and definitely we will look into it once. It's basically saying that if we are considering a TS plot, temperature and entropy, because at this point of time we are not even introduced with the concept of entropy, right? So let us not move ahead of time. So just, but the question states that we have to prove that in a TS plot, something similar to PV plot and PT plot that we have already discussed, we have to show that a constant volume line has a higher slope compared to a constant pressure line. Okay, we have to prove it. Okay, so let us not go ahead with go ahead of time, and let us just do it when the appropriate time arrives. Okay, so let us move to the next question. An ideal gas is contained in a container which occupies a volume of 100 centimeter cube. Okay, your volume is given and 25 degrees Celsius is the temperature at 180. Volume, temperature and pressure, everything is given. Oh, you can easily use the ideal gas law. It already mentions that it's an ideal gas. Oh my god, so simple. Find the number of molecules of gas in the container. Okay, very simple. Yeah, the only challenging thing in this question is you need to be aware with the concept of Avogadro's number. Okay, so let us go to the solution. It's again quite simple. You need to find the number of moles in the for the given pressure, temperature, and volume. Okay. So if you substitute the we use this form of the ideal gas law. It is PV. Sorry. PV is equal to N into R bar into T, because from this equation you can directly find the number of moles, right? So if we substitute the value of R bar, T, P, and V, because P, V, and T are already given, and R is a universal gas constant, and substitute it with the appropriate units, you will get that N is equal to 4.089 into 10 to the minus 6 kilomole. Okay. Now Avogadro's number is basically the number of molecules that we can find in a single mole of substance. Okay. 1 mole of a substance will include Avogadro's number of particles or molecules. Okay. So since the number of moles is 4.089 10 to the minus 3 kilomole, and the units of Avogadro's number is basic, and Na is given by 6.022 into 10 to the power 23 mole inverse, then you need to convert this in mole as well, so that this mole and mole get cancel out. So it is kilomole, so you can convert it into mole, so you will get it to be 4.089 to 10 to the minus 3 mole. So once you check out the calculations, you will get that number of molecules in this particular weather condition is 2.462 into 10 to the power 21. Okay. So let us look into the next question. The graph of a specific enthalpy and internal energy versus temperature for an ideal gas must be straight lines. So we just now discussed that since ideal gases are not calorically perfect gases, so in the case of caloric perfect gas, the plot of the specific enthalpy and internal energy will give you a straight line, because the specific heats are basically constant, so they are basically act as slope of those lines with an intercept of 0 in the y-axis. So this is not right, because since for ideal gas Cp is a function of temperature and Cv is a function of temperature as well, so this is false. Okay. For a perfect gas, Cp and Cv are, again I just now mentioned, so if you look into it, so our correct answer should be that they are constants. Okay. So bonus question was Cp and Cv. How does Cp and Cv vary for an ideal gas? So it's very simple. That, as I already mentioned, both Cp and Cvs are functions of temperature. Okay, in the case of an ideal gas. But there are many instances you get questions on numericals where they ask you to take, even while dealing with ideal gas, they ask you to take the specific heat constants as a constant value rather than taking it as a they ask you to take the specific heats as some constant value, but ideally they should be function of temperature in the case of ideal gas. But to simplify the calculations, they usually ask you to take the specific heats as constant in the case of ideal gas. Okay, but don't consider it to be generalized case, because in general they should be a function of temperature even in the case of ideal gas. Okay. So the final question is simple, match the following. So which of the following has been matched correctly? Okay, so Charles' law is this one. Boyle's law, Gay-Lussac law is this one. Boyle's law is this one. So since none of them are matched correctly, so the answer should be none of the above. Okay. So I think that's all from my end today. I'm sorry if there was some rush in the problem solving session part from my end, if at all there was some. And again, I'm sorry if I was not able to clarify any doubts that you had, because today's session was primarily dealing with equations and relations, dealing with that we used to deal with mixture of gases. Basically, so we were discussing mass fractions, volume fractions, these things. So this session was primarily involving many mathematical manipulations to find the appropriate form of equations to for a particular problem. So you'll see that eventually see that every type of problem will need certain mathematical manipulation that you yourself need to come out with. Okay, so the best thing as a that you can do beforehand to tackle such scenarios is to be well versed with these fundamental equations. Okay, if I go back here, the ideal thing for you to do right now is should be something like uh, be well versed with these equations, this set of equations that we discussed in the beginning part of today's session. Okay, I will eventually share these notes and it is also given in the lecture videos. So be well versed with these equations, okay, with these relations, uh, so that any type of question that comes uh, related to this type of equations, you will be able to handle. It should just be a simple manipulation of these equations. Okay, so don't get worried, because there's there's no single, what to say, single way of solving all types of different types of questions. Of course they depend on the same governing equations or the same governing principles, but since these equations can sometimes be a bit tricky to remember, so it's ideal for you to be well versed with these relations, so that uh, given that there may be questions that may ask you to tweak these relations a bit, so that you can get your desired form of the solution or desired form of the governing equation that will fetch you the solution. So as a suggestion or a suggestion from my end, I would suggest that you be well versed with these equations, solve the tutorial problems that was given by Professor Anand in the lecture videos. So there are 4 tutorial problems. It will be very wise of you if you go through all 4 of them once. All these 4 questions are truly quite interesting, as I myself found out it to be. So you can uh, uh, go through all of the these tutorial problems once. They are of different types, so you will be more well versed with this manipulation of equations. Okay, so I think that's all from my end today, and thank you so much. Okay.